Another concept that we have to be concerned about with regression equations is multicollinearity. Let's consider an equation where we have three variables: complaints, sales, and online sales. Our equation might look like the following. Predicted refund requests equal beta 0 plus beta 1 complaints plus beta 2 sales plus beta 3 online sales plus an error term. If two variables are highly correlated, they can impact the equation in such a way that they overstate the effect of the model. Now, this should be pretty obvious. If I have sales and I include online sales, which is similar or correlated to sales, it could overinflate our ability to do predicted refund requests, because it's almost as if the sales variable is included twice. So the model will end up having some problems. So let's take a look. On the right, we have a summary output of two regression equations. On the top, we have three independent variables, adding an almost duplicate of sales as x3. On the bottom, we have the two independent variable version. We can see that the r squared, not the adjusted r squared, has increased on the top from the bottom. So the top has 0.916 for the multiple r and 0.839 for the r squared. And you'll see that the multiple r at the bottom is 0.914 and 0.835. So the three variable model has a higher value for the r squared and multiple r. This is likely due to the addition of the variable. As we had said in a previous module, every time you add another variable, you will always increase your r squared and your multiple r. But notice that the coefficients have changed. We notice that the two sales coefficients have opposite signs, a common occurrence in multicollinearity. Also notice how the two coefficients are now not significant. The p-value is greater than 0.05. So multicollinearity will make the estimates of the coefficients unreliable, as evidenced on the right. And so not only will it increase its quote-unquote ability to predict, it may give you wrong values for the coefficients as well as for significance. So it's important to understand the variables that are in the mix. We can test for multicollinearity, but in Excel it's not quite as easy. Many statistical packages and add-ons for Excel should have a means to calculate the variance inflation factor. This is a number for each independent variable that indicates how much inflation of variance is due to that particular variable. Generally, numbers above 8 for the VIF would be considered variables with high collinearity. And we have a module that will actually show you how to calculate this in Excel. But here's an example output. So in the example before, we would have found this VIF for complaints as being 1.3, and for sales as being 24.6, and for the other sales variable, 23.8. As you can see, X2 and X3 have very high VIF numbers. And if we actually calculated the correlation between X2 and X3, we would see that it would be 0.99. So one way to test for multicollinearity is to examine the correlation between the two variables. If there is a significant correlation, then examine the signs of the coefficients. If they're opposite, you may have a collinearity effect. If this is the case, it is recommended that one variable be removed. Now, which variable should be removed needs to be guided by the analyst's determination of which variable is more likely to be the influencer of the model, since they're most likely not independent. So do we keep sales or do we keep online sales? The actual analysis is done by understanding what the variables do and what they mean.